So for high mass stars, we're going to start off with a lot of the same ideas. You start off with a main sequence, and I'm not going to go through the pie chart again because it's really just the same. Hydrogen, fusion, and the core. There are a few differences. For example, here's our sun as a main sequence. The high mass star is going to be much bigger. Larger stars have more fusion inside of them, and that's to support all of the extra weight of the star. And so they're going to burn through their fuel much faster. And the proton-proton chain is not fast enough. So what do these stars do? Is they do hydrogen fusion into helium, but they do it in a different fashion. They use catalysts to speed up the reaction, and they use 3 catalysts: C for carbon, N for nitrogen, and O for oxygen. So we call it the CNO cycle. That's how they do hydrogen into helium fusion. If you would like to see the steps, you can flip into the book and look at the figure. Okay? But these stars are so massive and they're burning through their fuel so quickly that their main sequence phase can only last for about 5 million years. Okay? Once helium builds up in the core, they're going to end up with shell fusion of hydrogen, which is not stable, and the fusion rates are going to skyrocket, and the star is going to become a red supergiant. And while it's a red supergiant, it's going to be very large, and it's not going to have the best gravitational hold on its outer layers. So this evolving star is going to lose a lot of mass from its surface, and this isn't going to last very long at all, maybe 100,000 years. I would like to disagree with the textbook a bit. They say that here, while you're burning hydrogen in a shell, that you should be a red supergiant for a 25 solar mass star. But really, a 25 solar mass star is actually still blue while it's burning helium. It's not like the 4 mass star where it's able to go all the way over to the red side of the figure here while it's building up helium in its core. So it would be technically a blue supergiant, but it's fine. If you say either way, you'll be fine. Once that helium core gets dense enough and hot enough, helium core fusion will start. Just like when we did this for the low mass star, we're still going to have that hydrogen shell giving you extra energy. The high mass star puts our sun to shame. These high mass stars just are so much more extreme and go through their stages much faster. This stage might last 1,000,000 years. So this phase is going to be generating carbon in its core. And this is where the high mass star becomes really different from the low mass star, because in this star, the core gets hot enough and dense enough that it can do carbon fusion. Right? And after carbon fusion, it's going to be hot enough to do oxygen fusion. So we're not going to call it a double shell burning star because it's going to be able to do lots more shells, burn lots more elements. So we're going to call it the multiple shell fusion supergiant. Okay. So once that carbon core can turn on, carbon will merge with the helium and it creates oxygen. Right? That builds up a core of oxygen, and eventually the oxygen is able to fuse, and the oxygen will merge with the helium and make neon. It'll make a core of neon. So let's flip over here to the end of the story. You're going to have your big, massive star, very unstable, lots of shells doing fusion at one time, dumping in a lot of energy. The star swells up and is amazingly huge. So you've got hydrogen fusion shell, underneath that helium fusion, carbon fusion, oxygen fusion, neon fusion, magnesium fusion, and silicon fusion. And all of that builds up to an iron core that can't do anything. I don't have all of these shells memorized. Right? You guys don't have to know all of these shells. What you probably should know, though, is that each shell is a heavier element, and it's fusing its way up to iron. Right? So it's going to fuse heavier and heavier elements until it gets to iron. And iron is a special element. It's a special case. Okay? This star is desperate for any source of energy that it can get, and it's using anything it can to try to support itself against gravity. So iron is what's really going to cause your supernova. Iron is the one element in the universe that you cannot get energy out of. So here's this graph, and on the horizontal axis is just every element on the periodic table. And vertically basically just means how much energy per particle there is in that atom. So hydrogen is really high up on the graph, so we might be able to get a lot of energy out of it. So if we fuse hydrogen into helium, you do a big jump on the graph. A big drop on the graph means that you can get a lot of energy out. But when you fuse helium to carbon, that's a smaller drop. It's not as good as a fuel. Carbon to oxygen, small jump, you'll get a little bit of energy out, but it's not a great fuel. And these multiple shell stars are going down through here, trying to get a little bit more energy out, a little bit more, a little bit more, a little bit more, until it gets to iron. And it can't go past iron, because if you make anything bigger than iron, it takes energy. So you get this iron core, and that's your death sentence for this star. Let's talk about pressure a little bit. Normal pressure is when the electrons and the atoms bounce around, and that bouncing is what keeps everything from being collapsed by gravity. Sometimes what's going to support your object against gravity is just the fact that electrons can't get packed any closer together. Okay? So your iron core is going to get held up by electron degeneracy pressure, but your star is still making more iron, and the core is going to get denser and denser, just squeezing those electrons a little bit closer together until they can't take it anymore. So eventually the electron degeneracy pressure of the iron core will just fail, and it'll implode. Gravity wins, and it destroys the electrons, and so that's your supernova. Boom. When the electrons get destroyed, they have to do something. So what they do is they merge with a proton. So all the electrons will merge with a proton, and that makes a neutron. So what you end up with is your iron core all turning to neutrons. And neutrons have no electrical charge, so you can pack them much closer together. So what used to be your iron core, held up by electrons, used to be pretty darn big. But now all of that matter can be packed much more densely, so the gravity can get much, much, much more extreme. So your massive star supernova happens when those electrons merge with protons. So that's these two merging together. And the core collapses into a ball of neutrons, and so those stay at the center. And in that reaction, it releases a whole bunch of neutrinos. Typically, neutrinos, we would say, just stream outwards and they escape. No big deal. Neutrinos can go through things and they just escape. But in this case, just the sheer numbers of neutrinos, we think that some of them interact with the outer layers of the star as they're being blasted out. And when the neutrino, which is going at almost the speed of light, smacks into that material, it gives it a little bit of a push. So we think that the neutrinos push the outer layers of the star outwards in an explosion. And in that event, it releases more energy, 100 times more energy than that star released over its whole life. The core of neutrons will be called a neutron star, but if gravity is allowed to, that can collapse further into a black hole, and we'll be talking about that later. So here's the Crab supernova remnant, and inside is going to be a neutron star. Okay, but we don't really see that right now. We're looking at the outer layers of the star that were exploded off. And these gases are called a supernova remnant. Right? And these gases are hot and they are still exploding outwards. Right? So they're going to cool and expand, and with time, eventually they'll become invisible. Here's another supernova remnant. The gases are still exploding outwards. And here's one that's far enough away that we don't have a gorgeous picture of it. But the explosion started in 93. And if you come back every few months, you can see how the gases are expanding. When it first starts out, the explosion is moving at 22 million miles per hour. The supernova remnants will expand and cool for hundreds of years, and eventually they will just become invisible and the gas will blend back into the galaxy. So we like to say that low mass stars can make elements up to carbon. High mass stars make up to iron. But there's a lot of periodic table beyond iron. And all of those took energy to make. So why do we have any of them in the universe? Maybe supernova? So during the supernova, so much energy is just trying to explode outwards. It's just looking for places to go. So during the supernova, there is more fusion. And so you can make elements heavier than iron. Nickel, gold, silver, platinum, uranium, right? All of those elements were created in really high energy events such as a supernova. And as it explodes outwards, it's getting returned to its galaxy. And so that material might mix back into the galaxy into a new nebula and eventually form new stars. I'm just going to cover the last section really briefly. It's about binary stars. So here's a higher mass main sequence star. I can tell because it's blue. And here's a lower mass main sequence star, a little tiny red dwarf. And they're just going to orbit each other for a long time. Okay. The high mass star is going to run out of its fuel first, and it's going to turn into either a red giant or a red supergiant. And if the red supergiant gets big enough that the outer bit of its layer feels more gravity from its binary star than from its own core, it will just flow over onto this star. This is called mass transfer. And what you're going to end up doing, though, is making this one less massive, which slows down its rate of fusion. It'll let it live longer. And what you're going to be doing is making this one more massive and speeding up its evolution, making it fuse its fuel faster. In the case of algal, this has actually transferred enough mass onto that little star to make it the more massive one. So now this is going to start running out of fuel faster, and eventually it'll become a red giant. And perhaps in the future, the mass will flow back in the other direction. Okay? These situations can get pretty complicated.